Great. So what we've done so far now, when it comes to this potato, is we have essentially looked at the displacement fields and boundary conditions that we apply there. We've looked at what happens in terms of being in equilibrium inside when you pull this little cube out, and see what kind of essentially stress components act on that cube and what are the conditions for them to be in equilibrium. We can now even start with the displacement field, check that the boundary conditions are satisfied or whether they're approximated only, and then essentially take those displacement fields, differentiate them, put them into columns, have the displacement gradient, take the displacement gradient, compute the strain matrix, go from the strain matrix to the 6x1 strain vector, map that with the constitutive relations, get to the 6x1 stress vector, and then check for equilibrium. That's what we have. The only thing that we can't really do at this stage is we haven't related how do we apply loads to the structure to how does it relate to stress components. So if I apply some traction or force on this structure to try and load it, how does that now relate towards, how does it now become sort of stresses inside the structure? That's the thing that's still missing. And this is essentially what I'm going to do in the next video, is just build intuition a little bit about what is these tractions and stress components first. I'm going to look at it sort of in a macroscopic scale, looking at a bar under uniaxial tension and compression, and just give you sort of an idea in terms of intuitive idea in terms of what's going to go down in terms of when we express sort of on the surfaces of objects tractions and think of those as stress components, how they are related. So that's going to be our first step, and then we'll develop that a bit further and then essentially have a formal relationship between tractions and stress, the stress matrix, and see what those relationships are, and then essentially we're good to go and say, all right, now we've got the generalized solid mechanics boundary value problem. That is the problem that we need to solve with finite elements, or at least approximate with finite elements, and that's going to be sort of a 15 equations and 15 variables. And when I talk about variables, I mean fields, functions of x, y, and z. Okay, so hopefully that gives you a good intuition of where we're going to go as we proceed. Thank you.